All right, in this video we're going to be looking at how to come up with your hypothesis and your null hypothesis or alternative hypothesis or whatever you want to call it. And of course our model that we're going to be testing is of course this one here. This will be our experiment, or we're going to be doing experiments and we're going to be testing to see if our experiment, the results match what our model predicts it would be. Now our model is this right here. All right, everything here is our model, and the idea is that these are the idealized model, the model that is our what we think, how we think the world works. And if given enough time, you would approach our model, as in you do millions and millions of experiments, and you would get closer and closer to the results predicted here, though you may never reach them. All right, so the idea, that's the law of large numbers. So that's a statistical law, and it means the more often you do the experiment or the more data you have, the closer you get to the idealized model of the world, what the real world looks like. And the idea is there's variance in the data. You don't get exactly the same thing every time. You get slightly different, so there's error involved. But supposedly, as you do more and more research or more and more experiments, you get closer and closer to the idealized model. And so the idea here is we use this kind of concept of a perfect model as what we call our expected. This is what we expect, and we expect what you predict here on the Punnett square from Mendel's model of peas, or in this case flowers. So the idea, let's review this real quick. Here's your male plant, here's your female plant, and they are both heterozygous for this particular trait. Now, heterozygous means a large letter and a small letter here, a dominant allele and a recessive allele in each parent. And of course, when you cross these, you bring them down and across, down from here, just one at a time, and across here one at a time. So here you get a big B and a little b. This is a dominant trait, meaning that it covers up the recessive trait so that you don't see the recessive trait. In this case, big B is purple, little b is white. So you get two big B's, you're going to be purple, of course, because that's all you've got, two big B's. Of course, when you bring these across, you get two what we call heterozygotes, and those individuals have a big B and a little b, with the big B covering up the little b. So big B being purple, these are also going to be purple flowers. So anywhere you see a big B, of course, you get a purple flower. The only way to get a white flower is to get two small b's. And when we work out these types of crosses, our idealized model, we get a ratio of 3 purple flowers to 1 white flower. So this is what we expect. We expect a ratio of 3 to 1. Now, is that what we actually get when we do an experiment? Well, we might. It is perfectly possible for us to do an experiment and to get these results. Now, will we? Probably not, because there's variation. There are things we cannot control for. There are unknown variables that are hidden. All types of things which might draw us away from this idealized model. But what we do is we try to make it as close as possible, and we need to test, all right, to see if we're close enough to make the assumption that we really are working underneath this model. And so that's what I've tried to explain in other videos. But here today, we're going to learn how to make the statement about this and develop what we call our hypothesis and our null hypothesis. So I'm going to switch from this, realize that this is our This is our expected model. This is what we expect to happen. This is the idealized model, our view of the world. This is how we think the world works, however you want to say it. And we expect this to be what occurs, and that is our hypothesis, at least, that this is a correct model. And we just want to know, if we do an experiment, how close can we come to this and still claim that this is what's really going on? Because there is some variation, there's some error involved, and so we don't get exactly 3 to 1. How far off can we get? Well, we've kind of looked at that with the chi-square. That tells us how far off we can get. But how do we state this in terms of what we call the hypothesis and the null hypothesis? And now this is important because you have to state it correctly to match up the verbal language and the mathematics. And I know that's hard to understand why that's so important, but believe me, it's extraordinarily important, and it's why so many people get things wrong in papers, and they get in trouble later on for claiming things that just were not true. They don't understand how to state the hypothesis that reflects both their mathematics and their theory. And we're going to try and combine those so you can understand how to make a statement about both the math and your theoretical assumptions at the same time. Now realize with chi-square we're comparing what we call ratios. We did a video on that. And in this case, we're the character under study, which would be flower color. And we have two different flower colors, purple and white. And we need to create a hypothesis and a null hypothesis. So the first thing to do is come up with a hypothesis. And our hypothesis here is that the ratios between purple and white is close to 3 to 1. Now, we could say that it is 3 to 1, but that kind of puts us in a corner. And yes, people can get around certain things using statistics, and they can lie with statistics. But in this particular case, this is the way we need to do it, and I'll explain as well as I can why we need to do it, and really why you have to do it. And then I'll explain why really statistics doesn't tell us that much. It really doesn't. And now it can tell us some things, but it doesn't prove things, and that's very key to the understanding of how to use statistics. Statistics never prove anything. They just kind of point you in the right direction and point out possibilities. Let's put it that way. All right, so the best way to state your hypothesis in our case would probably be that our ratio of purple to white is close to 3.1. We didn't say it was 3.1, we just said it was close. Now, a null hypothesis is kind of your counter argument, the opposite, if you want to think of it that way, of your hypothesis. So what is the opposite of the that the ratio of purple to white is close to 3.1? Well, it's that it's far away, and that it's not 3.1. And you use this. There's a reason for using the null hypothesis, because it is not possible to prove anything with statistics. Statistics never prove anything, and I want to emphasize that. And the reason is we're only sampling part of the world. And what you really want to say is you want to say this works everywhere. Well, it might not. Statistics are only saying that, hey, with this small part of the universe that I'm working with, and with the rules that I have here, and the experimental procedure that I've set up, this works. All right, and this is what happened. You don't prove that it happens everywhere. You don't prove that it happens under all conditions. You're just saying that right here where I'm at, what I'm doing, this works. And that's what statistics is trying to say. So because that's all you're trying to say, you can never say that you prove anything. All you can say is that, well, at least for me, it tends to work this way. And because of that, we come up with this thing called a null hypothesis. And the way to do it is very simple. If this is our hypothesis up here, all you do is add never right here. There are other ways to state this, but the null hypothesis are the ratios are never close to 3.1. For one thing, this is very easy to kind of mathematically, and I hate to say prove, but yeah, technically now we are kind of proving something. We're going to prove that, yes, this does happen. All right, in other words, the null hypothesis, the ratios are never close to 3.1. So all we have to do is, we don't want to prove it, but we do want to reject it. We want to show not that this has happened, but we want to show that there is a single case somehow that this did not happen. And that way we can reject our null. So the idea is to reject your null hypothesis, your hypothesis that that it never happens. So if we can show one case where it does come close to 3.1, we can reject the null. We can say that this is not true. Not that we're proving it, we're just saying that this one is not true. That's what we're trying to do. We're trying to prove, no, don't use that word. It's so tempting to use prove. We're trying to show that there is a case where the ratio is close to 3.1, showing that this statement is not a true statement. So if you think of it this way, once you get your null hypothesis, what you're trying to do, your experiment should be an example that rejects this statement. In other words, a statement that, if you want to say disproves the statement, that's fine. That would be superior to saying that you proved this. You disprove your null hypothesis. Or the correct terminology is that you reject your null hypothesis. And we reject that the ratios are never close to 1. All you would have to do is show one case of it, and you would show that this is not the case. This is not a true statement. So we're not proving anything. We're just saying that we want to show that this is not a true statement. All right. Let me state it this way. Trying to show that this is not a true statement right here. All right. That's what you're usually looking for when you're developing your hypothesis and your null hypothesis. And so it is very easy to reject it. All you have to do is find a single experiment where it is close to 3.1. And all we can do is show that in this particular case, things work the way we think they work, or they do not. That's really all you're doing with statistics most of the time. You're either showing that in a very specific case, things work the way we think they should, or things do not work the way we think they should. And when you try to, it's really hard to, don't do too much comparison. Usually if you're doing something that's statistical and it involves experiments, you really just need to try to keep yourself clear as to what you're doing. And this is something that's relatively easy to do. To prove, or to, if you don't prove anything, like I said, it's easy to mess up and use that word prove in there. But to show that something is greater than something else by a certain amount or something like that is really hard to display statistically, and it's very rigorous to actually do it. And most scientific studies are incorrect. They do it wrong. You can go look at papers, and if you really analyze what they say and what their numbers do, more than half are probably incorrect in their statements. Their general idea is probably right, which is why they get away with it, because in general you go like, okay, that makes sense. I believe that. But the way they state it is almost always incorrect. All right, to make a statement about our findings, we phrase it as a counter argument. So the null hypothesis is your counter argument. So you're saying that your ratio of purple to white is close to 3.1, and your counter argument would be that the ratios are never close to 3.1. All right, and that would be the best way to say it. And if our theory says that the ratios of should be the same, all right, that is exactly the ratio of purple to white is 3.1. Our theory says that this should be it, but in reality, you're never probably going to get 3.1 because as you add more data, there's always variability, and you're going to get something close to 3.1. It's just the way the universe works. These are not things that you measure that stay exactly 3.1 no matter what happens. Instead, they're probabilistic, and because it's probabilistic, because there are other factors controlling these ratios that are out of our control most of the time, but as a general rule, those factors don't affect it so much that you get very far off 3.1. But chance, it plays a role in science, and you have to account for it. But we can't prove this, so we cannot directly comment on it. Now, here's the idea. We don't make statements about the hypothesis because we can't directly comment on it because you can't prove it. So you really have to talk about something that you can actually say, when we did the experiment, we directly showed that this was the case, and you will never show definitively that you got this ratio, and that was the ratio, and that's always going to be the ratio. What you can say is that you can say this null and say never, and then get one that isn't and say, okay, well, we got one, so we can definitively say that this is not a true statement. So I'm re-emphasizing this many times because I want you to understand what you're actually doing. You are not showing this. You are showing that this is not true. All right, so that means we're never going to show something is exactly that. All right, like this, like 3.1. That's just not something you can do with statistics. So to make an honest statement, we have to say that there is at least one case, our experiment, where the ratios are the same. In other words, or that they are at least close to the same. In other words, if there's just one experiment out there in which is close to 3.1, we can actually say something about the null hypothesis. And that's exactly what you're trying to do. All right. And that would be an honest statement. All right. Now you can say one that makes both logical sense, mathematical sense, and is factually correct. So realize those are three separate things. Let me write those down. One that is a statement that is mathematically correct. Mathematically correct. All right, in the sense of it makes sense in the math. Logically correct. All right, and corresponds to reality, I guess, is one way to say it, but it's mathematically correct, logically correct, and all right, corresponds to actual reality. You can make errors in any one of these, and it sounds good, looks good, it gets passed in the papers. You can make mistakes in all three of these, and it still might be, as a general rule, correct, but it would not be correct. It would not be, like you said, an honest statement, but it would not be an accurate statement. All right? Now, statisticians use the trick to get the phrase to make logical sense and remain true in the mathematical sense, and that's when they use the hypothesis and the null hypothesis, because you can easily see that logically, all right, you can't have what? You can't have an example, a real-world example, that is close to 3.1, and this be a correct statement. So if in the real world I actually have an experiment where the ratio is close to 3.1. You logically can see that this statement is logically incorrect, and thus we can reject the null hypothesis. All right, so just make that clear that these three things are related and are necessary for you to make a good hypothesis and a good null hypothesis. All right. So if our hypothesis is that the ratios are always the same within a given margin in error, notice I put that error in there. The null hypothesis is that the ratios are always different by a large margin. All right. Now, so I kind of reversed this. Up here, I made a statement about using never, and here I made one using always. And you notice I put the always and the never in the null. So these are two different ways to make the statement, and they would both be correct. So our null hypothesis, the ratios are always different by a large margin. That is the equivalent of saying it is possible. Wait, where is it? The ratios are never close to 3.1. You could do something else, and you could do it this way. But notice that the always and never are in there in your null hypotheses. So to say something logically correct, all we have to do is say that we found a case where the ratios are close. That's easy to do, and it's what you should do in a good statistical study. But it doesn't sound good. And so people tend to try to use the word prove, or they tend to use other phrases that just are not honest in the sense of what statistics is actually telling you or what the math tells you. Now, they may be honest in the sense of the general gist of the paper is trying to show something that, hey, look, I think this is the way this works. Look what I found. And maybe it really does work that way, all right? But if you're incorporating the mathematics in it and what you can logically say from the mathematics, it would not be an honest statement. All right. So you cannot prove a hypothesis ever, all right, ever. But you can disprove its converse, the null hypothesis, and the tests we do, like the chi-square, allow us to disprove this null hypothesis. So the test lets us compare ratios and find out how close they are to one another. It's a measure, and it's an accepted measure of, you might say, how we measure what's close and what's close enough to fit the way we think the world works there too. So there are some hypotheses about how statistics work too. And what we're doing is we're saying, yes, we know it's not exact, but we're close, and from what we can tell, it means that we're close enough to say that, say, 2.8 and 3.2 are close enough to 3 and 1 that we will go ahead and accept that there was some error here and we are close to what we should have, and that this is the way indeed that the world works. All right. So then you can accept that your experimental procedures have validity. Now, this is something you can say. You can say that you accept that your experimental procedures have validity, but you still did not prove that your hypothesis was correct. You cannot say, again, that you've proven anything. You can say that you accept, that has different meanings, that your experimental procedures have validity. So don't say that you proved that your experimental procedures have validity, because you have not. I guarantee you that mathematically you have not proven that your experimental procedures have validity. You've gotten close, and so therefore you can accept that your experimental procedures have validity. And the reason we make this statement is because the word prove means something very specific in mathematics. And if you say prove, you are making an extraordinarily strong statement mathematically. All right, so there's being logically correct, and then there's something called mathematically correct. And proof is very hard to come by. And proof mathematically is extraordinarily hard to come by. Now, in general terms, in general language, proof is not that hard. It's almost there with belief, but mathematical proof is tough. All right, and that's why you can't say prove. You can accept your hypothesis to the extent that there is confidence that the sample is large enough and valid. This would also be a good way to state it. All right, this is a correct statement. Up here you can state that. And then here is the one that's the simplest and shortest and most to the point. If we have this case, you can reject your null hypothesis. So in other words, that's very simple. It's less complicated than these two sentences, but it essentially says the same thing, is that you can reject versus accepting your null, accepting your hypothesis, you could reject your null. And by rejecting the null hypothesis, you therefore are saying that that statement is not a correct one. All right, up here, like we did here, we said that we actually can mathematically prove, if you have a real world case of it being close to 3.1, you have logically made this an incorrect statement. All right, and that's why you can reject your null hypothesis. And this is the best way to say it. You rejecting your null over the accepted ones. Notice how much shorter it is. Very simple, straight to the point. You reject your null. Now realize you can reject your hypothesis if you're over that magic number on the chi-squared. You can reject your hypothesis. You probably shouldn't. Instead, you should say you accept your null. All right, so either way, this, you would say you reject your null if you are under the critical value in chi-square, and then you can accept, you can accept the null, all right, if you are above the critical value. So those are two different things. Most of the time we're wanting to do this. This is the one we want. All right, we do not want this one. Though you could arrange your hypothesis and null hypothesis to want the others, but I think the easiest way for the experiments that we're doing is to do this. You go through and either accept or reject your null and base it on your critical value and make your statements very similar to the ones that I've made here. This works for the genetic model that we're using for the flowers. There are other ways to state these, but I think for our model this is the easiest and the safest, and the one that you can you'll have less, it's less likely that you'll make a mistake and say something that's not true. All right,